Thanks everybody for coming out today. I'm Dave Winters, the big data architect within the data science and engineering team at GoPro. Just a little bit of background about myself. I always feel old when I say this, but I've spent 2 decades basically building backend systems within Silicon Valley, e-commerce backends, search relevance and ranking engines, corporate data warehouses. And we always ran into the same challenge, which was dealing with the data. You know, how do you ingest the data quickly? How do you turn it around and store it in a format so that you can then query it, allow the data scientists to query it in a quick fashion also. So we'll be talking about that today. We talk about the evolution of our GoPro data platform. And then specifically, we'll be talking about a feature of our data platform, which we found to be very powerful, dynamic DDL, which is essentially where we're adding structure to streamed data on the fly, and then allowing analysts to quickly query that data. I have a co-speaker. Hao, would you like to introduce yourself?
Yeah, my name is Hao, so I'm working at GoPro as a software engineer in big data. So before GoPro, I worked for the whole Hadoop ecosystem for like several years. So now, today I'm going to deep dive into the dynamic DDL, so after David, so thanks.
And if anybody wants to know it, yes, I did get that picture at Glamour Shots in the mall, and my wife did make me take my glasses off for it. But let's go ahead and get started. This will be, we're gonna go relatively quickly on this talk. Generally this talk takes about 40 minutes or 50 minutes, so I'm gonna go through real quick through the background of just what kind of data we're dealing with here, and then I'm gonna jump right into the architecture and then hand it off to Hal. He's gonna take a deep dive and actually go through some code with the dynamic DDL feature that we have. So let's start off just with GoPro, just where basically this data came from. Company's been around about 14 years. It literally was started with this guy, Nick Woodman, our CEO and founder. He literally took an SLR camera, shoved it in a Ziploc bag, and went surfing with it on a trip to Mexico, a surfing trip. And he just went crazy with developing this idea of a waterproof camera for action sports. It was basically he and a lot of friends and family that developed this. And then after a while, they started the GoPro Sponsored Athlete program, which was like hundreds of athletes, rock climbers, mountain bikers, snowboarders, even conventional sports people, tennis players, pro football players. They would take these cameras, just beat the crap out of them, give them feedback. And that was good for developing one camera, got us to about $1 billion of revenue. But today, the product line is much more complex than that. We have multiple cameras, we have a drone, we have a controller, we have software also, a lot of really high quality software which is provided for free to our end users. Apps that can run on both desktop systems and mobile devices to edit and share your software, excuse me, your content. So obviously to do something like that, you can't just have a few people use your products and get some feedback. You really need to get a large amount of data. You need data from millions of people, the millions of GoPro users, and so that's why we developed this. And so this was about 3 years ago. This was basically the diagram that we came up with, which was a GoPro data analytics platform. You'll see on the left and the bottom, those are all GoPro devices, GoPro software. We control how we get that data, and so we use streaming for that. We prefer to actually ingest the data in a streaming fashion. We get it quicker. You don't have the big spikes when you're processing the data, and that's always the way that we go internally. Unfortunately, we have a lot of third-party data, all of those sources at the top there, all your standard ones for analytics related to web and mobile and social media, ERP and CRM systems. For those, we're at the mercy of those third-party sources. So we don't know what format it's going to be. It could be a CSV, it can be XML, it can be JSON, you name it, and we don't control the cadence. So they're usually kind of slow. Sometimes you get lucky, you'll get them every hour. Oftentimes it's once every 24 hours. But we bring all of that into one platform, create the relationships so that we can join it together. And then the output, of course, is the product insights, which is going to be Tableau, it's going to be Plotly, tools that data scientists can build dashboards with. And there's, of course, we push data to other systems, such as CRM systems, so you can do your standard campaign management, otherwise known as spam cannons, push alerts on your mobile devices, those sorts of things. So as we went through this, there's a lot of challenges we found, and I'm just going to go through this one pretty quickly, but basically we're dealing with lots of different hardware and software that is sending us different types of logs. The variety of the type of logs are also anything, again, from JSON, XML, CSV. We even have packed binary proprietary formats which come from our devices. We have a variety of ingestion mechanisms, as I spoke about, so that some of the data is streamed in, which is our preference. Some of it is a batch pipeline, which we have. Then at the fourth bullet point there, we got to still seamlessly bring all this stuff together, make sure that we have foreign keys and so forth to join the data together. And then last, but actually most importantly, there's the PII, which is something that we've been very aggressive with from the beginning, with this hashing out, removing, encrypting the PII based on the various countries' regulation and codes that we have these days. So with that, I know that was kind of quick. We'll slow down a little bit here, but I'm going to push through, and we're going to talk about the actual architecture. So this is what I colloquially refer to as our old file-based pipeline architecture. It's actually our second version of our GoPro data platform, maybe like GoPro Data Platform 2.0. The original one was literally just a giant single cluster, essentially a data lake. And it had a lot of problems because you were doing 3 workloads. You were doing ingestion, you were doing ETL, and you were doing your analytics all in one cluster. So the typical scenario was an analyst goes on, fires off a big query, maybe it was a poorly written query, bring the cluster to its knees, the I/O spikes, and your ingestion dies. So one of the first things we did in this 2.0 architecture, and this is going on actually close to 2 years ago now, was we separated the workloads into 3 different clusters. And so you'll see that in the upper left-hand corner, we have our real-time cluster. That is where we are streaming in the data. That is primarily GoPro data sources. So it's going to be cameras, it's going to be drones, it's going to be the applications that run on both mobile devices and desktop systems. We have more control over the formats of the logs, but we don't have that much because the hardware teams, the firmware teams really dictate the format of those logs. Especially on the devices, they have very limited compute power and very limited memory and storage. They do have, it is a fully functioning Linux operating system that most of our devices run, but they still have those limited resources. And so because of that, they do use a lot of proprietary packed binary data files, data logs, which makes it pretty interesting for us when it comes to streaming those logs. That cluster is built with, the technology stack is basically has a RESTful service in the front end. We use that to do basic authentication from the client, which could actually be a camera itself, or it could be a GoPro app. They push logs to us. We do some authentication. As I was saying, we grab those logs. We stuff them into Kafka as fast as we can. From there, we have a series of Spark streaming jobs that process those logs. The very end, which is basically the output from that real-time cluster in the upper left-hand corner, is going to be a nice normalized flattened JSON file. Lower left-hand corner, we still have a batch induction framework, as we call it. We've got all those third-party external data sources. So we're at the mercy of basically all of those third parties for that as to what format it's in and their cadence. That we use a combination of Airflow and just a custom-built framework that we built that basically can download files either from S3 buckets, SFTP sites, or from a RESTful service. Same thing here, could be CSV, XML, JSON. We normalize it during our pre-processing to a flattened JSON format. And same thing is basically those 2 arrows with the JSON, those are a copy, and it's a distributed copy, copying the data to our ETL cluster. When you look at the streaming cluster at the top there, the processing happens fairly quickly every 2 seconds or so, but the actual copy to the ETL is anywhere from every 30 minutes to once every 12 hours, just depending on the data source. The lower left-hand corner, there are a few jobs that go once an hour, but mostly those are happening about once every 24 hours for the batch jobs. So the ETL cluster is where everything meets up. At this point, we're going to do 3 things. We're going to take those flattened JSON files. We're going to convert them into a columnar format, Parquet, and then we're going to use gzip compression. We tend to create pretty wide tables. In fact, we do a lot of pre-joining to try to reduce the joins that our analysts have to do. Again, speed up query execution. And because of that, you're going to have a lot of repeating values. So the compression ratios are pretty impressive. We also do a lot of pre-aggregation at this point. Because again, if we know that someone doesn't really care about maybe at the event detail and they want it aggregated at a higher level, we're going to pre-aggregate that to speed up the queries. So those are the 3 functions of the ETL cluster. It was originally built using 100% Hive MapReduce, and then has slowly been migrated to Spark, obviously for just performance for the most part. At the end of that, the output from the ETL cluster is going to be Parquet files with DDL. And so that means at that point we've added the structure to the files. The next step is fairly straightforward. We're going to do the distributed copy over to what we call our secure data mart. We use Impala as the in-memory execution engine. You can use the same, pretty much the same HiveQL syntax, some extra functions that Impala includes, and it's going to run in memory and be a lot faster. We also use Sentry, combination of Sentry, Kerberos, and LDAP to basically make sure that the right people are looking at the right data there. At that point, the data is available via ODBC, which works well for most of our analysts because the top tools that folks like to use at GoPro for the analytics folks are going to be Tableau, it's going to be Plotly, it's going to be Hue, and then some Python and some R. So now we're going to take a bit of a deeper dive here into just each one of those clusters. So this first one, this is our streaming cluster here. So this is that real-time streaming cluster in the upper left-hand corner in the last slide there. So AWS, 100% AWS from the beginning here for the GoPro data platform. So we have an ELB, Elastic Load Balancer, which sits in front of a pool of Tomcat servers that can automatically scale up with your AMI image, which works well, especially during holiday peaks or even weekend peaks, which is when the GoPro devices are used the most and we get the most logs. The Tomcat servlets servers just run pretty simple servlet, does that basic authentication from the device or from the application, grabs the logs, sticks them into Kafka, and then we start off that basically circular process there of Spark streaming jobs, pulling logs, doing some pre-processing, then sticking it back into yet another Kafka topic. And we'll dive into that one just a little deeper in just the next slide. While we're doing that, we start to write the event data to HBase. That's how we accumulate our state data. So almost all the data we get is our events. It's like a time series database, you can think of it, or a series of just timed events that are coming to us. So we accumulate it in HBase. And then we ultimately write the events into HDFS on that real-time cluster. The writing can happen anywhere from about once a minute to about once every 5 minutes. And then we finally do the distributed copy anywhere from once every 30 minutes to once every 12 hours, depending on the data source, to the ETL cluster. So this is going just a little bit deeper into that circular relationship you saw between Spark and Kafka there. So this is how we actually process the data in Spark. These are all Spark streaming jobs. Again, you have the ELB, you have the Tomcat containers there running our servlets. It's pushing logs into a root Kafka topic there. You have a root Spark job there. First thing we do is we take care of PII. So that means we remove it, we hash it, we encrypt it. It all depends on what the rules are for that particular type of PII. The next thing we do is we start to route the logs. It's usually based on what we call data source, but it can also be other rules involved there too. As you kind of work down that tree of Spark streaming jobs, you see those Kafka topics are in between there. When you get to that last column of Spark streaming jobs before HDFS, that's where we slow everything down. So most of the cadences or the batch intervals we're using for the Spark streaming jobs are about every 2 seconds. That last column there is where we slow things down because of what I like to refer to as an impedance mismatch. What happens is Kafka loves those tiny little messages, about 1K. If you read any of those benchmarks that like LinkedIn years ago and Microsoft wrote up on Kafka, they always use about 1K messages. So Kafka's perfect for that. But of course, HDFS and S3, they want huge files. They're in the gigabyte size. So we slow things down here, start to batch it up in that last column of Spark streaming jobs, and then wait until we have a nice large amount of data, and then write large files out into HDFS. So now we're going to jump into the ETL cluster. So we've already created the nice flattened JSON files, all normalized from the real-time streaming cluster. Now we're into the ETL pipeline. So of course we've got, on the ETL cluster, we've got the batch induction framework in the bottom. And so that's waking up via Airflow once every 24 hours or so, once an hour for some of the data sources, pulling down various log files. It's doing its normalization into a nice flattened JSON format, and it's writing that into HDFS. Same thing at the top here, we're doing a distributed copy from our real-time cluster for all the streaming data sources. Now we kick off Hive. Hive with some Spark. And basically we're doing that three-step process I talked about earlier, convert it to Parquet with gzip compression, do pre-joins, pre-aggregations. We end up with the structure in the Hive metastore, the Parquet files right there within HDFS, and now we're good to go. And we pull down, actually, at the same time, our state data, which we've accumulated in HBase so far, and also pull that into Parquet files with the Hive metastore DDL. And so now we're good to go. Now we just want to replicate that to our secure data mart and allow our analysts to start to query it. It gets a lot simpler here. You've got basically the copy of the Parquet in the Hive metastore, and basically you just allow Impala and Sentry to protect the data if you're Sentry, and Impala just to do the in-memory SQL execution, and we're delivering data to all of the applications which support ODBC. So there's definitely a lot of improvements with, this was the GoPro Data Platform 2.0. Isolation of workloads, ingestion separate from ETL, separate from analytics, fast ingestion with the support for streaming, secure by using a combination of Kerberos LDAP and Apache Sentry, fast delivery with Impala and in-memory, as long as you have enough memory, that is, and loosely coupled servers, which was great. You could take down the real-time cluster, do some maintenance, and end users can still do their queries and vice versa. Bad things, multiple copies of data, minimum of 3 copies of the data on 3 different clusters, tightly coupled storage and compute. If we need more, let's say, processing power on the SDM, the data mart cluster, well, you got to add more nodes to it. And, well, you might not need more storage, but, homogeneous nodes, you're adding more storage too, and vice versa if you needed storage instead of compute. Lack of elasticity, if you want to add those new nodes to a cluster, usually takes a couple days for HDFS to catch up on the under-replicated blocks. So basically just a lot of operational overhead of managing multiple clusters here. So last slide, and I'll hand it off to Hal. This is our GoPro Data Platform 3.0. It is in production. It's running in parallel today with our 2.0. We're still in the verification stages and cutting over to it. But one of the first things you'll notice is that we still have those 3 main clusters. We have the real-time cluster for streaming in the upper left-hand corner. At the very top there, you can see we have the ephemeral ETL cluster. Now, of course, it's ephemeral now because it can actually go away. We don't need it all the time. Sometimes it's sitting idle, and instead of us paying for it, it actually will go away. And then same thing with the secure data marts. We now have multiple of those. The other big thing is the dynamic DDL, which Hal is going to lead us through in just a minute here. Instead of writing out the flattened JSON files as we did previously, now the real-time cluster and the batch induction framework are creating both the structure automatically, the DDL, and the Parquet files on ingestion. And so what that means is actually as soon as that data lands into S3, it is immediately available for querying from all of our data marts. And then we have the ETL, which runs periodically still to do the pre-aggregation and the pre-joining. Other things is now we are using a Spark managed service, cloud service. We're using Databricks. And what that also allows us to do is have the elasticity for those clusters. So no longer do we have to worry about, oh gosh, the analytics teams coming to us going, man, our queries are just dying, they're running too slow. We can literally have the clusters automatically scale up, or we can even set up new clusters for them very quickly. So with that, I'll hand it off to Hal. I think I'm pretty close on time. I think we should be good.
Thank you, David. So now I'm going to deep dive into our dynamic DDL architecture. So before I deep dive into that, I want to show you guys revisit this high-level architecture of our streaming cluster diagram. So it's like everything remains same. So I want to show you guys where this dynamic DDL happened. So it's happened right after we got our data from Kafka. So we already got some existing topic. So if the topic structure has been changed by the data provider, we will directly, automatically change our existing table structure to reflect to the incoming data structure. So this will happen automatically. So whenever you got the data, you already got all the structure from the incoming data. Even the incoming data structure is changed. So from this point, you probably wondered, okay, what is dynamic DDL? And why we need dynamic DDL, and how we did this. So the definition of dynamic DDL is pretty simple. It's nothing but adding the structure on the data. It's on the fly whenever the data provider are changing their data structure or not. So as David already said, we don't have a control of our data. So we are not our data provider. So our data provider changing their data structure constantly. So without this dynamic DDL, what we used to do is we have to manually update our existing table to reflect the new change of the data structure. Then we have all of our aggregation cycle. So we have lots of aggregation cycle. So that usually takes a month, several hours to update all the aggregation cycle to reflect the new structure. And we always want to faster ingest our data. So whenever the data comes in, we want to make it immediately available for the user. So that's why we need all this happen magically, automatically, and will soon reflect to the user. So how we did this? We are using Spark SQL and the data frame API. So in next slides, I'm going to show you guys an example to show the comparison between our fixed schema concept and the dynamic DDL. So with the fixed schema context, we can also solve the data provider changing their data structure constantly. But compared to the dynamic DDL, it's really, it's kind of like will be difficult for the data analytics. So take a look at this example. So this is really a JSON format, simple entry. There's some record key and a record value. So there will be 4 attributes for this input JSON record. So there is a ID, first name, last name, and state and city. So what we used to do, we flatten this data first into 4 records, because there is 4 attributes in the data. So then this one entry after flatten the data become the 4 entry. So we use the record key and the record value as the attribute. So after flatten this single entry to 4 entry, we basically have the fixed schema. Basically, it's a record key as a column name, record value as a column name as well. Then we got the table here. So this table will have 4 columns, ID, log TS, record key, and the record value. So this is okay. If the data provider are changing their data structure, adding a new attribute, we simply add a new entry for the data. However, this brings some difficulty for our data analytics and the data scientists. So if they want to find some particular event, they want to find what happened for the particular event, what do they have to do is they have to write this big chunk of SQL to pivot this table like this, basically using the actual key as the column name and actual value as the column name as well. So this becomes a disaster for the data analytic. I feel sorry for them to write this big chunk of query. We should prepare our table immediately for them. That's why we introduced this dynamic DDL. So with dynamic DDL, we directly get this table. So in next slides, I'm going to show you guys a couple of snip of codes to show how we did this. Okay, so first we add a partition column. This has nothing to do with the dynamic DDL, but it's always good practice for data engineer to add a partition for the data, especially when your data grows really fast. So then we manually, we use Spark SQL to create the table. So the reason we are using Spark SQL here instead of data frame API to automatically create a table, because there's a bug in Spark. So if you are using data frame API to directly create the table, so the table schema will get out of sync with the metastore. So you have to use the Spark SQL to create a table. So after that, basically you need to find the new columns that exist in the incoming data, but has not yet exist in the destination table. So we found the new columns, then we alter the table, we alter the existing table, add the new columns. So it works in Spark 1.5, 1.6, but after we upgrade our Spark to 2.0, this syntax is stopped working. So basically, Spark 2.0 doesn't support alter table syntax, but I guess they already have some Jira ticket to keep track of that. I think they promise us they will support this in 2.2, but before this 2.2 released, we have to. There are several workarounds to work around this problem. I will show you guys 3 temporary ways to solve this problem in Spark 2.x in case you already use Spark 2. So basically, the first approach is you can launch a Hive Server 2 service, basically a separate service. Then you can use the Hive JDBC to alter the table. But I mean, you have to manage that service. The second way is use Spark to directly connect to the Hive metastore. So basically, Spark has some internal API to connect to Hive metastore and manipulate with Hive metastore. So the third way is you have to update the Spark source code and repackage that. So for us, we choose the second way. So basically what we did is we hacked the Spark code. We call some internal API to update the metadata. I'm not going to show you guys the details of how we did this, but if you guys are curious how we did that, you can talk to me offline. So, okay, so after we alter the table, we have this is really important. So we have to project all our columns for the table. So basically, you have to reorder your incoming data column to match the order of the destination table. The reason you have to do that is because if you append your data into your existing table, Spark will just use the position-based context to insert your data. Basically, it's not column-based, it's position-based. You have to reorder your data to make sure the data column from incoming data and the destination table is in the same order. And then then after that, you just append the data into your destination table. So here you have to, we use coalesce to control our partition. The reason we're doing that is because we have our partition key is based on the process data and the process hour. So we have a lot of partition. So if we don't control our partition manually, we have to, basically we will face some too many files open problem. Okay, so now we have all the code to ingest our data to dynamically alter the table, to dynamically add the structure into the existing table. I think we only have 2 minutes, so initially I want to talk about some repartitioning, but I think we don't have time, so that's it for us. We leave two minutes for the question.
Okay, we'll open up the floor now for question and answer, but first let's give our speakers a round of applause.
We do. Yeah, and it's purely for, the question, just in case everybody could hear, is do we still slow down the writes? And we do just purely because we want those large files. We don't want to end up with that small file problem, which we are all familiar with, killing the name node if you're using HDFS, and it's even worse with S3.
For the dynamic DDL stuff, how frequently are new columns being added? Do you guys support non-backward compatible changes, like changes to column types and things like that?
So how frequently, basically, it's not so frequently, but it's kind of like might happen like once a week, sometimes like that. So yeah, and you also have another.
The other question was, how do you handle like a backward compatible change to a data model? Like a named key gets changed from a numeric column to a alphanumeric column.
So basically, all our column currently is we cast them to string. So we don't distinguish with the column type. So we don't have that kind of problem. So basically, all column will become string.
So what we've done is, in order to support the flexibility, we've put the responsibility on the data source providers. And so they know if they change the semantic meaning of a column, it's going to be up to them then to figure out exactly what they did. And same thing with the data types. It's for the flexibility, and folks have used a lot of Hive and so forth. There's a lot of ways to cast it and be able to check with regular expressions if they do those sorts of things. But yeah, that's the cost of the flexibility.
Thank you.
Any other questions? Awesome.
All right.
Thank you all.
Thank you.